Good morning, good afternoon, and good evening. Thank you for joining Open Source Security Day on Google Open Source Live. If you haven't attended Open Source Live before, it's a monthly web series where each month we explore a different topic within open source. And today, of course, is all about open source security. My name is Anne. I'm a program manager for security at Google, where I focus on open source security. And today I'm joined by my colleague, Dan.
Thanks, Anne. Like you said, my name is Dan. I'm a software engineer here at Google, and I can't wait to co-host today's amazing event covering all things related to open source security with you. Anne, could you please tell the folks what's in store for them today?
I sure can. We're going to talk about supply chain, dependency problems, vulnerability disclosure, and memory safety. We will kick it off with a talk from Dan, who's going to take us through supply chain security. But before that, we have a couple of housekeeping items.
All right, so a few boring things, and then we'll get to the fun. Don't forget to put your questions in the live Q&A forum below the live stream window. Speakers are ready to answer your question live, so you don't need to wait until the end. If you're viewing in full screen, you will need to exit to see the live Q&A forum. Our sessions have been pre-recorded to allow for accurate transcripts in all the different languages, and so that speakers can focus on answering your questions live. Once we're done, at the end, don't forget to join us at the after party on Google Meet. You'll see a button to join in the event page at the end of the last session. And last but not least, use the hashtag GoogleOSLive to share your experience on social media channels.
And with that, let's head over to the recorded version of Dan. So, recorded Dan, take it away.
Hi, everyone. My name is Dan Lawrence. I'm a software engineer at Google on the open source security team. I'm going to be talking about open source supply chain security today. If you've heard of all of these different supply chain attacks in the news lately, I'm going to be explaining what they are and how they affect open source software. So I'll start out by introducing myself a little bit. I've been at Google for about 9 years now, and I've had the privilege of working in open source software for about the last 6 years out of those 9. While working in that space, I've done a bunch of things in the container and Kubernetes area, and that's what got me started worrying about open source security, specifically supply chain security. So I started a couple different open source projects, and I've been doing a bunch of work over the last few years to try to improve the situation. And luckily, sometime in the last 6 months or so, it seems like everyone else has started paying attention to supply chain security as well, especially in open source. So that's probably why we're talking about this here today. If you're interested in reading any more of this stuff or seeing any of the other projects I work on and trying to make this stuff better, I tweet on Twitter, and there's my handle. It's LORENC_Dan. So let's jump into today's topic. I'm going to start out by describing what I think are the two main problems with open source software, open source security, and supply chains today. I'm going to cover what you as an individual or a company can do about them to protect yourselves today, and then what I think we as an industry need to do about them going forward. So I'm going to start out with the two problems, like I said. The two problems with open source, with the security of open source software, is that number one, open source software is open source. That means anybody can see it, anybody can contribute to it. This has a bunch of benefits, but it also has some downsides that I'll cover in a bit. And then the second problem is that just like all software, open source software is software. All software has bugs, whether I write it, whether you write it, or whether a group of people that you've never met writes it in an open source community. So these are kind of the two problems. They're right there in the name. It's open source and it's software. You have to address these two problems differently because they are different problems. So let's jump into those. Finally, when you start looking at supply chains too for open source software, there are threats everywhere. So we've got these two problems, the fact that it's open source and that it's software, and then it's a very complicated supply chain here. So at every single one of these points, every time something gets handed off from a developer to a source code repository to a build system, these are different places that threats can come in. So we've got to be looking at the problems with open source and software at every single one of those levels. So let's start out with the first problem. What do we do because open source software is open source? Like I said, it's not a problem that open source software is open source. There are just a lot of different things we have to fix because of it. Open source software is free. It's one of the biggest reasons people use it. But sometimes just because it's free doesn't mean that it's free to you. Sometimes free is not worth it. Sometimes the problems that it comes with actually cause more problems than it's worth. Second, anyone can contribute. Well, anybody that spent time on the internet knows that not everyone on the internet is nice. There are people out there trying to insert bugs. There are people out there trying to find problems in open source supply chains and attack it. So just because lots of people can contribute and there might be lots of eyeballs on something doesn't mean that the source code is secure. It's really easy to use open source. This problem has crept up because sometimes it's too easy to use. If you're at a company, you might not even know all the open source you're using. This comic here on the right kind of depicts that. All the modern infrastructure that we see is kind of up here at the top. These are all the things you think you're using. You might not have any idea all the open source that's powering those things on top that you're looking at. And a lot of it ends up being maintained by a single person, thanklessly, that you don't even know, and you might not even realize you're using this software. So because it's free and it's so easy to use, you can get yourself into some tricky situations here. Finally, there's this belief that open source is transparent because you can see the source code. And this is true, except how many people are actually looking at the source code for all the open source they're using. Most people are getting open source through package managers, downloading binaries. Very few people are actually looking at all the source code and building it all themselves. So in reality, the source code is transparent, but the way a lot of people are consuming open source makes it opaque. So let me cover some examples here of attacks at every single one of these levels that we just talked about. This is a brief history. It's just over the last year or so. And there are probably a whole bunch more attacks that have happened since I made this presentation that haven't even been added here yet. It seems like there are new ones almost every single week that we forget to add. But I'll cover a couple of these and just kind of explain how they work and some of the problems they've caused. One of the scariest ones, going back to April of last year, and this is a recurring problem, is typo squatting. So this example here, there were 700 packages taken down for typo squatting on Ruby gems. This happens every couple months. Somebody does a research program and finds a whole bunch of packages doing typo squatting that are malicious, and they get taken down each time. Every 3 or 4 months, you see this across Ruby gems, across PyPy, NPM, all the different package managers. So typo squatting is a really tough type of attack to handle because it's so tricky. It's a form of social engineering. This is where somebody will upload packages with names that are designed to sound official and trick people into downloading these instead of a real one. They're not always typos. We see this with Google packages sometimes, where we have a package that might be named like Google Cloud Storage or something like this, for example. And an attacker will upload something maybe that uses an acronym or uses some Unicode characters instead of the O's in Google. So you might see like GCP Cloud Storage or something silly like that that's been uploaded by somebody else. So it's impossible for us to think of all the different permutations and Unicode characters that people can use to try to trick people. So you have to be really careful in making sure that you're installing things only by their actual official names. You see this also happened in September of last year on NPM. And the malware there was actually used to steal people's PII from a database. So stuff can be pretty serious. NPM, the node package manager, sees a lot of attacks in general. It's also one of the most commonly used ones. So it's hard to tell if it's a problem with NPM or if it's just directly related to the usage. We've seen some other scary attacks here in NPM. Because it's so easy to install stuff and you might not know that you're pulling it in, these packages can do a whole bunch of bad things. So one of the other examples here is setting up reverse shells. Open source software is pretty easy to install inside of your CI system, so people do that constantly. And this program this was the one in October of last year I'm referring to, set up a whole bunch of reverse shells, which give an attacker direct access to your CI system during a build. And people were able to go in and steal secrets from the build systems that way. Another really scary one here, because open source is free and maintainers aren't getting paid, is the Great Suspender extension compromise. So this was a Chrome extension called the Great Suspender. It was one of the most commonly used ones in the Chrome store. And what it did was, what it was designed to do anyway, was suspend tabs that you weren't using for all the people that have thousands of tabs going on their computers. So this would suspend them and try to save battery life on your laptop. Somebody built this by themselves and maintained it for years, and eventually sold the rights to this extension to someone else. So it was open source on GitHub, but after it was sold, the buyer took it down off of GitHub and started building their own version and publishing it to the store adding some malicious code. So it wasn't present in the GitHub repository. It was being present and inserted into the build system. So that way the binary published on the Chrome store had some of this malicious code. It was eventually taken down when people discovered it. This is a case of open source being free, being hard to make money off of, which can sometimes lead to bad incentives and people taking advantage. There have been a bunch more attacks in the last couple months. There was a paper from the University of Minnesota that's gotten a ton of attention lately. What they were trying to prove is that it was possible to insert bad commits into the Linux kernel. So they took commits that they knew had bugs and tried to get them reviewed and inserted. This sort of backfired and led to a whole bunch of bad publicity and everything like that. But it is clear that this type of thing can happen, especially in large projects. And then a whole bunch of other scary ones here that I'll go through quickly. Microsoft's VS Code, popular text editor. This attack was actually reported by a researcher, so it wasn't something malicious, but this could have been one of the scariest ones in recent memory if it was bad. But an attacker was able to use some misconfiguration in the VS Code GitHub repository to get commit rights and to merge code into a release branch of VS Code that would have made it out to people's installations. If an IDE or something like that gets compromised that developers are running all over, then you would have to kind of lose trust in all of the things that IDE has built. That would have cascaded very quickly, but luckily it was a researcher who reported this rather than someone malicious. More typo squatting, and then finally, one of the biggest ones of this year, it was the codecov.io attack. So codecov.io is a code coverage service that provides free coverage reporting over time to open source projects. Unfortunately, the way that a lot of people use and integrate codecov into their CI systems is with a bash script that they use curl to grab from codecov.io/bash website. Codecov unfortunately leaked some of their credentials in their own CI system, and an attacker was able to find those and serve malicious scripts that stole secret environment variables from CI systems. CI systems are known for having quite a few secrets in them, especially things to publish other artifacts. So CodeCov had to notify all of their users, and anybody with CodeCov in their CI systems should have had to do a scrub and make sure that all secrets in there had been rotated, and anything that those secrets had access to have been audited. This is not a new thing. Supply chain attacks have been happening for a while, but they are accelerating, and they're going to get bigger and worse over time unless we do something about it. So now that I've hopefully scared you, but not too much, what are some things that you can do to protect yourself when you're using open source software? A lot of this is obvious, but it is hard. So you kind of just have to do the best you can. Step one is know what you use. This sounds obvious, but it's not always that easy. If you're a developer and you haven't looked through your vendor tree or your dependency configuration file for a while, some stuff might have crept in there that you don't even know. If you're installing a couple dependencies, those dependencies have a couple dependencies, and this kind of blows up exponentially pretty fast. If you install a couple things, you might end up with 500 in there. You might trust the dependencies that you're using, but unless you trust the full transitive tree of all of their dependencies, you can end up out of control. So this is really hard, especially when you start building artifacts and publishing them and combining those artifacts into other artifacts. It gets pretty hard to keep track too. If you're practicing something like continuous delivery, you might actually have a couple different versions running in production of your own application at a time. If your application dependencies are changing, then you can see that the combinatorics start to get pretty tricky. And you might end up with a whole bunch of different versions of your application with different versions of dependencies. When a vulnerability gets reported, either something unintentional or something malicious, if you can't quickly figure out exactly what you're running in production, you can get into trouble. So step one, know what you use and be able to look that information up as quickly as you can. Once you've done this, you're actually in a pretty good spot. A lot of people aren't able to answer those questions, especially not quickly. So step two here, once you know what you use, to take it to the next level is be able to control it. Be in control when new dependencies are added. Continuously audit them, continuously compare the old dependencies you're using to vulnerability databases and look for old bugs. Implementing governance and control about all of your dependencies, whether they're internal or open source, is really one of the best ways to protect yourself so things can't slip in without knowing about them. And this applies both to your code as well as your build system. When you're inserting new tools and services and things like this in your build system, you really want to be reviewing those and treating them just as seriously as the rest of your production system. Your build system is what gates the code that you're building into production. So the security there of your build system needs to be at least as high as your production environment. And then finally, if you really want to take it to the next level, is stop consuming binary packages. You don't know what's in them, and in most places, it's pretty hard to verify any of this stuff. Very few projects are doing things like reproducible or verifiable builds. So you're really trusting a third party to compile things correctly, to not insert any malware, and to secure their own build systems. So if you really want to take full advantage of open source and the transparency and the visibility, you want to build what you use directly. This is really, really hard, so you don't need to do it all or nothing. You can take some of the dependencies you have and build those, some of the most critical ones. The point of open source is to be able to change it and compile it and build it yourself anyway. So this also sets you up to take advantage of a lot of that stuff. Half of the battle here really is knowing that you can build it if you ever have to, if there's ever a vulnerability you find that you can't get fixed upstream, or if there's ever a change you need to make that you can't get upstreamed. Being able to add that patch locally, build it, and get it out to production quickly shows that you're in control and that you can react to stuff quickly. So, as an industry, what should we all do though? These things are mostly about protecting yourself, not really improving things for everyone else on that last slide, which is kind of against the whole point of open source. So there are a lot of things that we can work on together as an industry to make this easier, to make it so everyone doesn't have to worry as much. I think the first one is to make it all easy. Security is not a priority for the average open source developer, or the average software developer in general. Security is an afterthought, unfortunately. Um, so by making it as easy as possible and as automatic as possible, we can make people actually do the right thing by default. This means we need to build new tooling, data, and use all the crypto that's out there to start securing supply chains that people aren't doing today. Um, there are update frameworks that are secure that we need to be using instead of curl pipe to bash, but curl pipe to bash is so easy and people keep doing it. We need to make these secure mechanisms as easy or easier if we want people to actually start adopting them. And you want to require this for your own company, right? Lead by example. Back to that first slide. If you start requiring your developers to only use things that are built responsibly and implement these security best practices, then you can actually spend time helping upstream to implement these so that you can use it. This is definitely going to be easier than writing things yourself. Nobody can stop using open source completely today. We're way past that time. And then finally, normalize supporting maintainers. There are a lot of models here. You can try some. You can fund maintainers, you can help them, you can send patches, you can sponsor a project, you can get your logo on the page. There's a lot you can do here. And then finally, interoperability of metadata, right? Once we get people to start producing all this metadata of their build systems, what commits they're using, what build tools they use and everything, we want to make sure we can exchange this across the industry. The Continuous Delivery Foundation, which Google is a sponsor of, has a working group that's focused solely on interoperability of supply chain metadata. So some of this work is amazing, and some of the most popular build tools out there are adopting some of these new formats so we can exchange all of this. So that covers the problem with open source, the open source portion of open source software. And that's really mostly relevant to supply chain attacks, like I showed on that first slide. The second problem, though, and why a lot of people kind of throw up their hands and say, why should we even bother fixing the supply chains, is that open source software is software. It's full of bugs, it's full of CVEs that can be exploited. Some of those bugs might be malicious, but for the most part, most of them are not. They were inserted by accident, but people can still take advantage of them. So what do we do about that problem? I'll start with showing some examples here of some pretty scary ones that have happened. And all these were not malicious bugs. They were just things that were put in by accident that people found later and took advantage of, or didn't if they were reported responsibly by a researcher. A lot of these famous CVs get cool logos like this and websites set up, which helps them get popularity, but not all of them do. These are just some of the ones you might have heard of. Heartbleed was one of the biggest open source vulnerabilities that was found, and really raised people's awareness of this whole area and the whole problem of the open source ecosystem not having the support it needs. Heartbleed was a bug in OpenSSL, one of the most commonly used libraries for securing internet traffic. And it had been in the project for years, and it was possible to exploit this to steal secret credentials and inspect traffic that people thought was secure. It's a pretty simple fix, but it had been present for years, and we don't really know the impact of it. Um, Apache struts. This is a slightly more boring one. This is a serialization library, which are always known to have problems because they're processing untrusted inputs. But one of these led to a remote code execution flaw. This happens all the time. It's no big deal, except the problem here was that people did not update their Apache struts correctly. And this led to the famous Equifax breach, where they didn't update their Apache struts, and an attacker was able to steal a whole bunch of data because of this remote execution flaw. Shell shock is another scary one. These bugs can happen in even innocuous programs like your bash shell. This is an issue where a certain environment variable set up in bash, one of the most common interpreters out there on most systems, could be exploited remotely. So just by having a bash interpreter present in your program, even if you don't think you're using it, was able to lead to a whole bunch of remote code execution. There are countless more of these, but these are the type of bugs I'm referring to in this section. So even if you are building things from source and knowing what you use, you still have to worry about these kind of 0 days that are found and reported. Yeah, this is a kind of comparison between the bugs that start to get attention and what people actually have to do about them. What most people worry about, what you see, is these 0 days with the logos that I just covered on the last slide. Everyone wants to protect their systems from bugs they don't know about yet. These are the scariest ones that keep you up at night because they're kind of unknown unknowns. They're found by research firms. There's usually huge bug bounties involved. And there's a lot of research that goes into these. To deal with these correctly, you probably want to have a plan in place to deal with them. Figure out what you would do if a really scary 0 day is found in all of your systems. And this can be tricky if you're deploying software into customer environments all over the world and it takes you days or weeks or months to convince everyone to update. You want to worry a little bit more about this and have emergency playbooks in place for how to do updates faster if you need to roll out a patch. But other than that, you can't really control it. So don't worry too much about the ones you don't know about. The really scary ones here, the ones I worry the most about, are the known bugs. These are the old ones that have been sitting in code forever. This is the Apache struts. And if you have a lot of environments set up and systems running all over, it's easy to lose track and not know that you're running a server under somebody's desk that's exposed to the network, exposed to the internet, with a version of software you forgot to update. Just because you forgot about it doesn't mean an attacker won't find it. Right? These things are easy to find from the outside. So what you got to do is just keep updating things. Pay attention. Don't get lazy. Don't get sloppy. It's not exciting, but every organization needs to do this. You need to track what's running where, and you need to update it constantly. If you update frequently, the updates get easier, and it's kind of a self-rewarding cycle. Smaller updates or easier updates, which you can do more frequently, which make it easier to keep updating even more frequently. There's some pitfalls here, though. This is usually grungy, kind of more boring work that isn't rewarded, so nobody wants to do it. The easiest thing to do is reward this work at your company. Update, update, update. Automate this, make it as easy as possible, monitor it and track it. These are the embarrassing ones to get caught by too, because you have no real excuse. 0 day is something that hits the entire industry. Everybody using a particular piece of open source software, getting hit by a 4-year-old vulnerability in something that's been patched for 4 years as well. It's much harder to come up with an excuse for that one. So don't get caught by these. These are what everybody should be worrying about. So what can we do as an industry about this? I think one of the best things we can do to start fixing all the unknown bugs in all the software that we're using is to normalize working upstream. And I think it's probably about a factor of 100 to 1 if I had to guess, in companies using a package to companies that have ever contributed a patch to that package, maybe even more than that. Make that easier for your developers. Make it easier to send fixes. This has a ton of benefits, both to the open source project, the open source ecosystem, and to your company. If you're using, making a bet on a huge piece of infrastructure software, it's awesome to know whether or not you can get a minor bug fix upstreamed. You'll learn the development flow. You'll learn how the project works. You'll learn how they take security. You'll learn how they treat small bug fixes like this from important users. If you try this once on something small that you find, it'll give you confidence going forward. If you can't get something in, or nobody's responsive, or nobody's even there to review the code, that's maybe a signal you should take to look for a different package if something's been abandoned. Giving back and fixing bugs upstream also builds important bridges, and it helps improve the public good. There's a great blog post about this from Julia Evans when her company was evaluating using Kubernetes. She actually went and found some bugs and tried to fix them just to learn what the development process was like, to learn the architecture of the system, and it worked out great. So in summary, to wrap this up, open source software is just software. There's this common misperception that just because you didn't write something, or because something is published on GitHub and has a whole bunch of stars, that it's been well reviewed, it's been audited, it's secure, and people have found all the bugs. That's just not true. I've written tons of open source software, tons of stars, and there's bugs all over it. All software has bugs, not just the stuff you write or your company writes. And then supply chains are tricky. Supply chains are scary, and all the components of your supply chain need to be treated as critical production systems, because that's what they are. They gate what goes into your production environment, and so failing to protect these is like leaving the door wide open. Open source is great. I don't want to scare people away from using it, but some of the aspects that make open source great do make certain classes of attacks easier. These aren't things that are unsolvable. We just need to actually take them seriously and solve them. We can do this by working together as an industry and by supporting open source communities. It's easy, it's much easier than you think, and it's worth it. So I hope some of this scared you a little bit, enough to look into your own supply chains, but not too much. We can fix this together, and we're working on that here at Google and with a whole bunch of other companies. Here are a bunch of links and some of the projects that my team is contributing to help out here. I won't read all of these. We can find them later, but we're trying to make it easier to sign software in the SigStore project. We're trying to make supply chains hardened automatically in Tecton CD, finding bugs with OSS fuzz, and a whole bunch of other things. So thanks for listening today, and that's all.
Thanks, Dan. You know, I noticed on Twitter lately you've been using SigStore and just like signing all these artifacts ever since the project was announced. So, what is the coolest thing you've signed so far?
Well, our slogan is, if you can build it, we can sign it. But I think the most fun thing that we've signed so far has been WebAssembly modules. They're pretty fun to build and pretty fun to sign.
That's awesome. I think your GIF work isn't too bad either, so that's been fun to watch. Next, we're going to hear from Oliver Chang and myself talking about improving open source vulnerability management. So let's roll that tape.
Hi, my name is Oliver, a software engineer at Google, and I'm here to talk about some work we've been doing in the vulnerability management space for open source. So open source is widely used by pretty much everybody, which means that the security of open source is very important to the foundational security of the internet and software ecosystem as a whole. When a vulnerability is discovered in the software project's open source dependencies, the developers need to be promptly notified in order to remain secure and avoid getting exploited. Today, this is very difficult to do, as dependencies can span multiple package and language ecosystems. Handling dependencies can also be very complex because they are often part of large transitive trees of dependencies rather than being direct dependencies. There are also multiple vulnerability databases that they need to care about as well. So what ends up happening is lots of manual triage is typically required to stay on top of these, and new package versions which contain vulnerability fixes are easily missed. As an open source library user, there is no standard vulnerability format or database, or even tooling that can be easily used across different language ecosystems. Users have to handle each ecosystem and vulnerability database separately, with different parsers and version range handling for each. Some language ecosystems, such as NPM, have out-of-the-box support for vulnerable package detection through NPM audit, while others, such as Python, do not provide any out-of-the-box. There is just no common tooling or standard here. CVEs are commonly used today to describe vulnerabilities, but it's very difficult to use them directly to manage vulnerabilities in open source. The key issue is that a CVE often does not have any machine-readable fields that match reliably against the package name and a set of effective versions in that package manager. CPEs are commonly used in CVE entries to identify a software and version, but they don't map well to real package names. An example here is the CPE for a Ginger 2 vulnerability. The CPE refers to Ginger without 2 in the name, but the actual package name in the Python package repository is Ginger 2. Other libraries with numbers in the name do end up having the number included in the CPE. And in general, the names used in CPEs do not consistently match the package names and versions in real package managers. On the flip side, from a vulnerability database maintenance perspective, CVEs are also difficult to request and require lots of manual work to generate. As a result of these problems, there are many different vulnerability databases started up by different groups, such as GitHub security advisories, and there are also community-maintained vulnerability databases for language ecosystems such as Ruby or Rust, and then there are also non-free commercial solutions such as Snyk. So to try to unify vulnerability management in open source, we launched something called OSV, which is short for Open Source Vulnerabilities. It's a vulnerability database and automation infrastructure for open source packages. For each vulnerability, we track the precise version ranges that are affected and make it easy to match the package names. On the right, we have some examples of vulnerabilities we currently track. So this started with a completely automated dataset of a few thousand vulnerabilities from a continuous fuzzing service we also run called OSS Fuzz. And we've been working hard to expand our sources of data as well to include other package ecosystems. To consume this data, OSV provides a very simple ecosystem-agnostic API that allows users to query for package vulnerabilities by providing either a Git hash or a package name and version number. Git hashes are unique, so they're the only thing that need to be specified as shown in the first example. Otherwise, the package name and ecosystem name need to be provided along with a version string. This then returns any vulnerabilities that correspond to those input versions. We record and return vulnerabilities using a very simple and minimal JSON format. Here's an example of a fictional vulnerability in the Ginger 2 Python library. And the key feature of this schema is that we record very clearly the package name affected and the very precise version ranges using Git hashes and version strings that match exactly what's used in the package manager. We're also trying to standardize this format to be used for other vulnerability databases. And you can find the spec by going to tinyurl.com/vuln-json if you're interested in providing feedback. We've already engaged with many other existing vulnerability database maintainers, such as GitHub, for their feedback and incorporated them. Our ultimate goal with the schema is for it to be a simple interchange format that all vulnerability databases export. Services such as OSV can then aggregate all this information easily and then present a consistent view of all open source vulnerabilities to users. This will help reduce missed vulnerabilities and promote common tooling that works regardless of language and package ecosystems. The Go team is already planning to adopt the schema for their upcoming vulnerability database, and we've made progress with the Python and Rust communities as well to export their vulnerabilities in the same format. So making it easier for users of open source to consume vulnerabilities is just one part of the story. We need to have quality vulnerability databases with precise version data in the first place, which usually requires lots of manual triage work. To help with this, OSV also provides automation tools to help with determining impacted version ranges, as well as scraping existing vulnerability feeds. For vulnerabilities with machine reproducible steps, OSV will perform bisections automatically to determine both the commits which introduce and fix the bug. From there, we can look at repository tags to determine the list of versions that are affected. This is how every vulnerability from OSS Fuzz is triaged, with no human involvement in the entire process. And here we have a real example of a vulnerability entry where an OSV Gitbot appended the list of affected versions given the input commit ranges. And finally, for vulnerabilities that aren't easily reproducible, we've been building tools to reduce the manual workload required to triage existing vulnerability feeds, such as CVEs, and extract as much version information as we can. And we also try to match these to package names and package versions. In cases where version data isn't readily available, we try to parse vulnerability descriptions to extract version numbers, make sure the valid version numbers in the package manager, and output them in our formats. Some manual triage work is still required, but we're building a workflow where this is minimized as much as possible. And we're planning to use this to bootstrap a community-owned database of Python vulnerabilities very soon. And that's about it. If you want to read more about some of this work, here are some links that you can explore. And now I'll hand it off to Anne, who has been working on developing a framework for handling vulnerability disclosures in open source.
Awesome. Thanks, Oliver. So Oliver was talking about how to find known vulnerabilities that affect your project, but what if your project is where the vulnerability originates? We're going to be talking about how you handle that. When you get that email that says, hey, I have found a security issue in your open source project. The process we're going to be talking through is coordinated vulnerability disclosure, and we'll go over what that is. We're going to go over how to set it up if you're an open source project maintainer. And if you're a user, keep paying attention because you might stumble across an issue as you're using this project, and it's really important that you know what this process looks like and how to be involved in it. And a caveat that this is the condensed version. There is a lot to vulnerability disclosure, and if you're going to implement it for your project, there's a handful of decisions that you need to make. Fortunately, we put this all up on GitHub. So if you head over to github.com/google/oss-vulnerability-guide, you will see a huge reference guide with tons of material there. There's a runbook if you just want to know step by step, tell me what to do. And then there's templates, which we're going to go over in a little bit as well. So I keep saying coordinated vulnerability disclosure. Vulnerability disclosure actually has many models. There's not just one. There's multiple processes for verifying, communicating, triaging, documenting a vulnerability. Some of those you might hear are full disclosure, which prioritizes getting out information as quickly as possible and as widely as possible. And you might also hear private disclosure, which prioritizes keeping information on a need-to-know basis. And you might hear things like silent patching involved in private disclosure. Coordinated disclosure is a model that acknowledges that both the product or project owners have some wants and the reporter does as well. And those two groups are going to have to work together to figure out how they protect users, avoid compromise, but both end up getting a solution that works for both of them. So let's walk through the life of a vulnerability in CVD. Don't worry, you don't need to take the slide in. We're going to go one by one from the first step of intake all the way through to disclosure. So let's start exactly at that top. This chain kicks off when someone finds an issue and decides to notify the project team. So here is our researcher. It's actually my dog. He got a promotion for today, but here he is. They found something shouldn't behave this way. They want to know, how do I contact the right people in the project? So let's talk about that right people group. Who is that? Who is that? You probably want to set aside a small group within your open source project to be the people who will respond to email or however you're going to set up your intake, respond to those intake reports, and deal with coordination and triage. It doesn't have to necessarily be all security engineers. These aren't necessarily people who are going to fix the project. They're really on just the hook for taking in reports and triaging them. I should also mention, some open source projects might only have 3 people total working on them, in which case you are the vulnerability management team. The other thing is that you want to put this information in an obvious and easy place. By obvious, I mean don't nest it under something like /governance/community. Your researcher is probably going to give up before they find that. And then you're going to have just, a loose vulnerability on Twitter that you really wish you would have had some early heads up about. By easy, I mean don't add any more friction to this process. The reporter has already done you a favor by deciding to notify you. That's fantastic news. So don't do things like adding new tools that you only use for this one purpose or multiple steps. Email is actually really quite fine. It fits all those boxes. If you are going to use one of these tools, having email as backup is a really good idea so you can make sure that people can get a hold of you if for some reason something goes wrong. This information should all live in what's called a security policy. And if you're a frequent GitHub user, you might be familiar with this as a security.md file. This information should say how to reach the VMT, what to include in your report, and it's really important that you set response expectations. You can kind of think about this like a customer service interaction. If you send a ticket in asking for some help and you get radio silence for a week, you're going to assume that nobody's there to help you, and you're either going to give up or find a different way to get your issue out there. If you at least get, hey, thanks, we got your report, we're going to take a look at it. You know that help is on the way, even if you didn't get all the answers in that first interaction. So the issues come in, it's acknowledged, and then assessment starts. So not everything is actually a vulnerability. Vulnerabilities need to give undetected access or compromised data, and that typically falls in the categories of data integrity, availability, or confidentiality. Saying this is a bad design decision or here's a suggestion for improving security are not vulnerabilities. Those are things that can be handled in the open in public issues for your project. When we do see that something is not working as intended and gives that unintended access, then we do have a security vulnerability. And what do we want to do with it? We want to patch it and get a CVE like Oliver was talking about. So researchers have lots of different reasons for finding issues. Don't just assume that they're going to send you the issue and they have no interest in helping you or no interest in figuring out what the patch is. They might actually be very invested in finding that patch and working with you. So my advice is to always just ask. Let them make the call. If they want to help you out, be involved with that. And besides, it's open source. I don't think many of us are in a position to say no to extra hands. For that patching, you're going to want it to be done in a private environment that has restricted access. Everything needs to be logged and can be made public after disclosure. If you use something like GitHub Security Advisory, that meets those requirements. But in the guide, you can see some of the qualities you're going to look for if you're not a GitHub user. While the patching is happening, you're also going to want to kick off the process for requesting a CVE for the vulnerability. There's more information about this in the guide, but I really wanted to call out crediting the researcher. It's so important that we thank people for coming to us and finding these vulnerabilities and helping us out, and giving them credit for their report if they would like it is a very critical way to do that. So finally, let's talk about this 90-day thing. This is stemming from the coordinated part of coordinated disclosure. It's really important to have an agreed upon timeline. This means the reporter knows that you won't sit on their finding indefinitely. Reporters really like to see things disclosed and credited as quickly as possible. And if you do sit on it for some reason, they can go ahead and share that information because notice and time were given to address the issue. 90 days at a maximum is kind of that common etiquette. This 90 days starts when the reporter first emails or notifies the project, not when you get a chance to respond to them or when you get around to working on the issue. And the 90 days is really your maximum time frame. Closing issues much sooner than that is always preferred. I should also mention it's not universal. Sometimes, depending on the severity of the vulnerability or a researcher's preference, they might not want that. They might want 7, they might want 30. And so it's just important that you talk and figure out what's going to work for both parties. So now we have a documented issue, a patch, and a CVE. So let's get this thing ready to disclose. You might notice that I skipped embargo notification, which is up there as the 5th step. This is actually a really complex process, and it only applies to a small group of open source projects, typically when there's a robust vendor ecosystem around them. It's a really careful decision to do this with additional responsibilities, and so all that information is in the full guide on GitHub. When you're ready to disclose your project or your vulnerability, you're going to want to send out a security advisory. These should be very factual and brief, get straight to the point about what somebody needs to know, affected versions, how to mitigate it, save things like how I found this or this wild fact about how this vulnerability works for things like blogs and tech talks. There's also no point in hiding this information. Security through obscurity isn't really much security at all, and a user can't protect themselves from what they don't know about. So putting things on your mailing list where it's appropriate, setting up a security advisory page, those are all really good ideas. And there's nothing wrong with having a lot of CVEs for your project. It doesn't mean that your project is full of security holes. It means you have a really robust response to responding, finding solutions, disclosing, and moving forward and hardening your project. So it just helps everybody the more we can have this information public and shared. And of course, we want to give our reporter a heads up before we do the disclosure, and again, thank them. It's just such an integral part of the process. And there you have it. We have taken a reported vulnerability from being a reported issue to intake, assessment, getting a CVE, patching, and then finally disclosing. So the TLDR, particularly for the project maintainers here, is to have a plan before you need a plan. Know who's going to take in issues, who's going to respond, templatize those communications as much as you can, and really get that security policy in place. That's how researchers will know how to report issues to you. And inevitably, you will get something, and don't panic. Researchers are human. It's a good sign that they contacted you. It means that they want to see this through a resolution. They want to work with you. So say that thank you, take a breath, and walk through your process. And if you're a project user, it's important that you know where you should be looking for security announcements. How do you stay up to date on this project? What do you do if you come across a potential vulnerability yourself? Be familiar with the process and where to report. And of course, in the spirit of open source, take a look at your team. Is anybody good at organization, communication? Does someone have incident management experience? And can you help out with vulnerability management for the projects that you use? So there's that guide where you can read more in depth about all these things and find the runbooks and the templates. I really love seeing open source projects have effective disclosure practices. So you can find me on Twitter for any questions, comments, and the occasional dog photo. So thank you so much.
Thanks, Oliver, and pre-recorded Anne. I love terrible jokes, and your talk gave me an idea for one. Do you want to hear it, Anne?
Do I? Okay.
Knock, knock.
Who's there?
Your dependency chain.
Your dependency chain who?
Well, that's just it. You don't know who your dependencies are, do you?
Dan, that's terrible.
Next, we'll hear from Nikki Ringland about open source insights, understanding your dependencies. Take it away, Nikki.
G'day! My name's Nikki Ringland. I'm a product manager in Google Cloud, and I'm joining you from the Eora lands of Sydney, Australia. Today, I'm going to give you an overview of Open Source Insights, a new initiative helping developers explore and understand their dependencies. Creating software has become more and more complex. Developing using open source libraries lets developers build things faster, and organizations can be more nimble. We all can be more productive. Open source essentially stops us from having to reinvent the wheel. But while adding a dependency might mean less work than writing it yourself, it's not no work. Open source software is much more dynamic than the old way of working, and it's hard to keep up with. And that brings with it a bunch of ongoing maintenance burden. At its core, Open Source Insights is an accurate dependency graph model for open source ecosystems. We aggregate information on dependencies, security vulnerabilities, licensing, and other package health metrics, enabling tools that support building safer and more robust software and products. Because just like old Captain Napkins here, dependency problems can get pretty hairy. We've got an API and a website and some exciting planned integrations, and I'll give you a sneak peek demo shortly. But first, let's take a step back. What do I mean when talking about dependency problems? Let's say you're writing package A. And to do so, you depend on several other packages that provide some functionality. And they in turn might also depend on packages, and so on. But if there's a problem deep in your dependency tree, say a vulnerability or a package with an incompatible license, that might have consequences for your project. The problem isn't isolated to package K. It could affect D. It could affect any leaf within this tree leading between it and me. And worst of all, it could affect me because of a problem in a leaf package I've never even heard of. And if the problem with K is a license incompatibility, your whole tree is infected by this license. So understanding your dependencies is critical. Understanding what's in them and how they interact with each other is important. And identifying anything surprising that might bring is a key part. But understanding these dependencies isn't always easy. In some languages especially, dependency bloat is a common or even unavoidable challenge. Having good dependency hygiene can be really hard. Now, each ecosystem is a bit different, but looking at NPM, a packaging system with over 1.6 million packages, On average, each package has 12 direct dependencies and nearly 300 indirect dependencies. Making sure you understand what's in that graph is a really big task. And adding to the challenge of the sheer size of those graphs is the fact that those graphs are constantly changing. Now, a quarter of all published packages on NPM have a change in their dependencies every day. So for an average 300 transitive dependencies, you know some of them are probably changing daily. That makes for a lot of upkeep. But why does it matter? Well, build times, download or checkout times, maintenance, testing, deployment, updating, security, licensing, compliance. These are all things that might be affected by the scale of your dependency graph. You need good information, supported by good tooling, in order to understand and be able to make good choices about your dependencies. When a new version of a package is released, it might have changed its dependencies. And if you depend on it, even 17 layers deep into your graph, your dependencies have changed. Now, different systems have different opinions on stability versus freshness. And in practical terms, this might mean pinning, where updated dependency versions don't automatically cause a change in your project. But maybe you want those new changes. Perhaps it was a patch for something bad. Even if you pin your graph so nothing ever changes, a new vulnerability might come to light tomorrow that affects your whole tree. Vigilance is required. And we might like to think of our graphs as looking like this, nice orderly trees that are structured and clear. In reality, dependency graphs are complex directional graphs. They're intricate, and they can grow increasingly, outstandingly, terrifyingly large. Here we see NPM, and this delightful mess is a rendering of Kubernetes dependencies. So looking at the size of these dependency graphs, it's clearly a very complex task to keep a handle on it. It's simply beyond human comprehension. And this is really important that we do, because we know that there's stuff in the graph that might be problematic. In 2019, a study by researchers at the Technical University of Darmstadt found that 40% of all published NPM packages depend on code with known vulnerabilities. And these are scary numbers, but not unsurprising. After all, big packaging systems have big challenges. And in many respects, NPM are leading the way in tooling to help developers face these challenges. NPM Audit is a valuable tool to discover what you have, what vulnerabilities you have in your dependencies. But what do you do then? Some other systems are also developing similar tools, but they're not quite there yet. We need tooling now to help you understand what's in your dependencies and what that might mean for your project. So we're going to start our web demo at deps.dev. We can see on the right here the number of package management systems that we support: NPM, Go, Maven, and Cargo, with NuGet and PyPI on the way soon. Now let's say for this demo that we're interested in a particular web framework called Express. We'll click on it and we'll get an overview of the metadata and other information that we can use to understand this package and its dependencies. First off, we can see whether it's impacted by any security advisories, in this case not. We can get an overview of the licenses, both the license that it itself has and a summary of the licenses of all of its transitive dependencies. We also have information about the number of dependencies, both direct and indirect, and the number of dependents. In this case, we can see that it's quite a popular package to depend on. Over here on the right, we've got more metadata about the package itself. When it was published, a description, an overview of its owners, links to the package and the projects as well. And finally, at the bottom of the page, we have an overview of the event history. And this will include when new versions are released, a change to the default version, and also anything like ownership changes. Now in this case, let's say we're not interested in the most recent version of Express, but instead a slightly older version that we're still using, 4.15.5. When we click to look at that, we can see that it's impacted by a security advisory, specifically in its dependencies. We'll click on more details to find out more. Now on this page, we can see an overview of how this vulnerability affects us. We find out that the vulnerability itself is in the MIME package. We see which versions of that package are affected and unaffected. On the left here, we also have some metadata about the vulnerability itself, with links to more information, a short description, and information about the severity if available. Now this is very interesting, but we want to know how this affects us and our use of the version of Express. So let's take a look at our dependencies for Express. Here we have a list view, and we can see that MIME 1.3.4 is the issue. But actually, in order to understand our dependencies, this graph view is a much more useful tool. So in this case, let's filter our dependencies to just the paths that lead to the problematic MIME version. We can see that there are multiple ways that we depend on MIME, and so fixing this is probably going to be a quite challenging issue. It wouldn't simply involve updating one version, but multiple versions of different dependencies. Instead, what we might want to do is change the version of Express. And in fact, up here, we can click on the Compare tab to compare different versions of a package with one another. So in this case, we've defaulted to the version that we're using and the most recent version, although you can compare any version you'd like. We can see a comparison in a diff style view as to when the versions were published, their licenses, and in this case, what we're interested in is the security advisory. We can see that the security advisory in the dependency, here, MIME 1.3.4, is no longer affecting the most recent version of Express. That's great news. But we also want to look at what else has changed in the dependencies. And we can see that there's actually a not small difference between the two versions. So this might warrant additional security review just based on a change in dependencies. So that's a quick overview of some of the ways that you can use this website to understand your dependencies of open source software a bit more. And since our whole infrastructure is built on Google Cloud using open source software, we found it to be a really valuable tool in understanding our dependencies and the impact that they have. To be able to make good choices about your dependencies, you need access to the right information and the right tooling. Now, I want to call out a few key information components here. Vulnerability information is a critical component. Developers want to know if they're using a package that is affected by a vulnerability. That is, the specific version of that package is affected. But some older vulnerability formats, like CVEs, typically only include whether or not a package is impacted, not which specific versions. And that might mean more noise than signal. We're happy to see and use the shared vulnerability format for open source packages outlined in the spec here, tinyurl.com/vuln-json. It's machine readable and allows for easy automated matching of package names and specific versions. Ultimately, having really precise security information is critical to enabling developers to understand what needs to be fixed to build safe software. But vulnerabilities aren't the only thing you might want to consider when deciding whether or not to depend on a particular package. The OSSF Scorecards is an initiative of the Open Source Security Foundation, a cross-industry collaboration to improve security of open source software. Now, the scorecard defines a set of metrics and provides automated security scores for them. The goal is to automate security posture analysis of OSS and proactively help improve the posture of critical open source software. Metrics include things like whether or not a package follows code review or signs release artifacts, or whether they pin their dependencies. This information can be used by developers or organizations to make a better judgment on whether a package should be trusted and depended on. We include these scorecards for packages that have them as a good way of highlighting information so that developers can make good decisions about their dependencies at a glance. So today I've shown you a quick overview of what we're working on with Open Source Insights. And there's lots more in the works too, including supporting more package management systems like PyPI support. We're really excited about how this data can be useful for developers and the open source ecosystem. Now, maybe you're all too familiar with dependency problems, or just now have become curious about what your dependency graph actually looks like. With this new view of your dependencies, who knows what you'll discover. Check out our preview release at deps.dev and get in contact. We'd love to hear from you.
Thanks, Nikki. We've really seen dependency compromises in a big way recently, so I'm very excited about all the work your team is doing. Next, we're going to hear from Josh Ose about working towards a memory-safe future. Over to you, Josh.
Hi, my name is Josh Ose, and I'm the Executive Director of Internet Security Research Group, or ISRG. ISRG is a nonprofit that was founded to serve as a home for public benefit infrastructure. We like to run digital services that improve privacy and security for everyone. We're probably best known for Let's Encrypt, our certificate authority. Today, Let's Encrypt is helping more than 260 million websites enable TLS to protect their visitors and themselves. We also do some other things though, and today I want to talk about our memory safety initiative. Since our inception, we've been thinking a lot about how to run secure digital infrastructure. One of the biggest problems we have is the frequency and severity of vulnerabilities that are found in the internet's most critical applications. Most of these vulnerabilities are what we call memory safety vulnerabilities. The interesting thing about this type of vulnerability is that we know how to eliminate it. We could, with some considerable effort, make memory safety vulnerabilities a thing of the past. We just need to do the work. I'm not going to get into the details of what memory safety means today, but at a high level, a memory-safe language manages memory properly for programmers. Languages that are not memory safe depend on programmers to manage memory correctly. When memory isn't managed properly, mistakes can lead to security vulnerabilities. Since even the best programmers frequently make mistakes, programs written in languages that aren't memory safe are much more likely to have serious security flaws. When we talk about languages that are not memory safe in the context of internet infrastructure, we're mostly talking about C and C++. So the software that we use on the internet is relatively unsafe from top to bottom because of how widespread use of C and C++ is. So at the top, the closest to users, we have web browsers, which are typically many millions of lines of C and C++. From there, we have servers, more millions of lines, proxies, business logic, cryptography, image processing, and kernels. Pretty much everybody's running either the Linux kernel or the Windows kernel. Again, millions of lines of C. So almost every deployment stack at every company and organization contains a ton of C and C++ code all throughout the stack. The vulnerability situation has gotten a little out of control. So Google estimates that 90% of Android vulnerabilities are due to a lack of memory safety. Microsoft estimates that 70% of all vulnerabilities in their products over the last decade have been caused by a lack of memory safety. And whenever you look at lists of 0 days or patch notes and things like that, a huge percentage of the vulnerabilities are due to memory safety. So society pays the price for this every day. It's privacy violations, financial losses, denial of service, human rights impact. These vulnerabilities have a real impact on people's lives and our society. So if we're going to have C and C++ code around, and we will for at least a long while, we should do our best to make it as safe as possible. And fuzzing and static analysis can help with that. So there are a lot of great efforts out there to put together tools that make C and C++ code safer. And that's fantastic. But they introduce a lot of overhead. They're sort of applied inconsistently. And ultimately, they don't solve the problem. So these are really worthwhile investments, but it's not what ISRG is focused on. We're trying to work on a more complete long-term solution. So we know how to solve this problem. That's what makes it so frustrating. Like I said, so many vulnerabilities are due to memory safety, and it's not like it's a problem we don't know how to solve. It's just a lot of work. We have to replace the code that isn't memory safe with code that is memory safe. We know how to do it. We have the tools. So let's get to work. And even if it takes us 5, 10, even if it's 15 or 20 years, the internet is not going anywhere. We have a long time horizon for these kinds of big investments to pay off. ISRG's Memory Safety Initiative has 2 goals. The first goal is to move the internet software infrastructure to memory safe code. The second one is to change the way people think about memory safety. We view our role as consisting of the following parts. We want to come up with a strategy. We want to help facilitate and coordinate the execution on that strategy. We want to help raise the funds for the people to support the people who are doing the work. And we want to help communicate about what we're doing and the problem space in general. So our engineers may do some of the work, but mainly we'll be enabling community and maintainers to do the work. The first part of our approach is to identify projects that have the best return on investment potential. So we're looking for projects that are very widely used. We're looking for projects that are particularly security sensitive. An example of something we think about there is what's sitting on the network edge? What's the most exposed to the world? So on the efficiency side, we're looking for projects where we can replace key components with existing memory safe libraries. So when we can do that, it means that we don't have to write a bunch of new code from scratch. We can just swap out some old code for some new code or some other code. And we're also looking for maintainer and project cooperation. It makes it so much easier when you can get maintainers on board with a plan. So this brings us to slide number 2, which is we want to work with maintainers whenever possible. Maintainers have really valuable knowledge about their software and the people who use it, but they also have the ability to ship memory safety updates to existing users. If you can't get a maintainer on board and you can't change software that already exists, you have to build competing software and get users to switch to the safer version. That is much more difficult. We would so much prefer to work with existing maintainers and then be able to ship updates directly to users without them having to do anything except run the update processes that they should already be running. So in order to do that, part of what we need to do is find funding for maintainers. It helps us create buy-in and lets them know that we appreciate their time and their effort and alleviates resource concerns. And we're making a big ask here. We're asking them to introduce new languages into their software and change how components of it work in pretty considerable ways. So it's only fair that we help support them when they do that. The third thing I want to point out is that we really prefer a modular approach. It usually doesn't make sense to go out and rewrite an entire piece of software in a different language that's memory safe. We'd much prefer to do it piece by piece. So we want to encourage projects to replace libraries or module functionality with memory safe libraries rather than ground up rewrites. It breaks it up into manageable pieces and allows us to deliver value incrementally. So if we can just swap out one library for another and deliver that via software update, we can sometimes do that in a matter of months. If we were rewriting the program from scratch, we wouldn't get that kind of incremental value. We might have to wait, 1, 5, 10 years, who knows. Also, when we have a modular approach, we can focus on investing in libraries that many different pieces of software can use. And when we improve those libraries, it improves lots of different software. Over time, we want to build trust with maintainers by building up a series of success stories. So it's, when I talk to maintainers, it's totally understandable to me that they have a lot of questions and concerns about what it means to start moving to memory safe code. And part of convincing them that they can and should do this is showing them a series of success stories and say, here's a previous maintainer that had similar concerns to you. Here's how we talked through them. Here's the solutions we came up with. And hopefully this makes other people feel more comfortable with moving forward. So I'm going to talk about some of the projects that we're currently working on. The first project on the list here, and the first project we embarked on, is curl. And I'm just so happy with how this turned out. So we identified curl as a really popular networking tool and library. It's in cars, it's in microwaves, it's on desktop computers, servers, it's all over the place. And it's a network tool, so it's on the network edge dealing with untrusted data quite often. And it has a really great maintainer. So we reached out to a guy named Daniel Stenberg who maintains curl, and he had a bunch of questions and concerns about what moving to memory safe code might involve. They were really great questions, but he was open to listening, and we did a lot of listening too. And we worked together to come up with a plan that would not be disruptive to the existing users of curl, but that would add an option to use memory safe networking code. And then maybe someday that code becomes default when it's well enough tested, but people will still have the option to use the old code if for whatever reason they're not able to switch. So we came up with a plan that was non-disruptive. We were able to find financial support for Daniel's work, and this has just turned out really well. It's such a great success story and has really helped to make other maintainers more comfortable once we explained how this worked. The next thing I want to talk about here is Russell's. So Russell's is a TLS library. We're essentially trying to build it up to be a suitable replacement for OpenSSL in many applications. So when we first learned about Russell's, it was already a really excellent TLS library. And we have identified some things that can be improved. And then we talked to the maintainers about how we might do that and found the funding to help make some changes. So Russell's is just getting better every day. We're really excited about it. And I think going forward, one of the first things we're going to be able to do in a lot of critical networking applications is move to a memory safe TLS library. And that library will often be Russell's. The next thing on the list here is a perfect example of that. So Apache's HTTPD is a really popular web server. And it has a module called mod SSL that provides TLS services to the web server. So we're working on a replacement module for mod SSL, and we call it mod TLS. And the new module uses Russell's for TLS. So when you switch to mod TLS, you get a bit more modernized TLS module that uses a largely memory safe TLS backend. The last thing on the list here is the Linux kernel. It's very exciting to me that this is on the list at all, because when I started working on this project, I'm a pretty ambitious person who's willing to undertake big projects. But even I thought, the Linux kernel just might be too much. It was hard for me to imagine how we might make progress in bringing memory safe code into the Linux kernel. Then I learned about some work that Alex Gaynor and Miguel Ojeda had been doing, and it was so impressive. They figured out how to build certain modules in the Linux kernel in Rust. So primarily we're thinking about drivers here, but someday it could be other parts of the Linux kernel. They had written a lot of the code. They managed to get really great feedback from the Linux kernel community. It's just so impressive to watch what these two have done, and we're really excited to support them. So that was a lot of information about how we plan to actually move code, but I also mentioned that we want to change the way people think about memory safety. So we're going to be doing a lot of communication about this problem. Fundamentally, if you ask an engineer today to deploy, let's say, for example, a reverse proxy, even a security conscious engineer might reach for something like Nginx or Apache or something like that. That's just millions of lines of C. That's standard practice. And I think a lot of people, either don't have a choice or don't feel that they have a choice about the tools here. But either way, I don't think we think often enough about the risks involved in putting millions of lines of C or C++ code on the edge of our network and processing untrusted network data. I mean, we have decades of evidence that, if you got a million lines of C, you are definitely going to have vulnerabilities. So I'd like us to think more clearly about what it means to be making that choice every day and get to the point where we fully appreciate the risks associated with doing this and we start really investing in alternatives. So thanks for listening today. I want to make sure to thank Paul Kerr and Alex Gaynor for their work to bring dimension to this problem. my meetings with them and talking to them have been so helpful to me to understand, what are the problems that people are facing today, what's going to help move the needle in terms of how people think about these problems. I also want to thank Daniel Stenberg, Stefan Eising, Dirk Achman, and Miguel Ojeda for taking the first steps to really help start writing code and moving our infrastructure forward. And I also want to thank our funders, including Google, for understanding our vision and helping to make it a reality. And for understanding that open source maintainers need to be supported. Thanks so much.
Well, that talk was both a terrifying look at the state of open source security today, as well as a hopeful look at our new bright memory safe future. So thanks, Josh. And with that, that's a wrap. So it's now time for our after party. Come join us over there at the after party by clicking the Watch Live button on the event's agenda page to be redirected to our Google Meet.
Today's speakers are also going to be joining us, and we'll have some quizzes, interactive activities, and even a few surprise guests. So we hope to see you all there, and thank you so much for joining us at Google Open Source Live.